Hello everyone, I'm Vaibhav Gupta, and in this video, we'll briefly understand one of the most interesting ideas in computer science today called generative adversarial networks or GANs. And then we'll go over an example to understand how to generate images of handwritten digits using deep convolutional generative adversarial networks or DCGANs. In that code, we'll be using the Keras sequential API, which we used in one of our previous examples. So let's go ahead and understand what are GANs. GANs are an exciting and recent innovation in machine learning in which these are basically defined as generative models. That is, they create new data instances that resemble your training data. That is, GANs can create images that looks like the photographs of human faces, even though the faces don't belong to any real person. So what does generative mean in the generative adversarial networks? Generative describes a class of statistical models that contrast with the discriminative models. In the layman terms, a generative model generates new data instances, whereas a discriminative model discriminate between different kinds of data instances. A generative model could generate new photos of animals that look like the real animals, while a discriminative model could tell a dog from a cat. So these GANs are basically one kind of generative models. As you can see on the screen, it looks this this is a simple architecture of GAN where it has two components. First is the generator that learns to generate the plausible data. Um, and then you have the discriminator, which learns to distinguish between the generators created fake data from the real data. So these generated instances from the generator kind of becomes a negative training example for the discriminator. And each time the generator penalizes the discriminator penalizes the generator for producing the implausible results. So think of generator as an artist which learns to create images that looks real. And think of discriminator as an art critic which learns to tell the difference between the real images and the fake images. And, in this generator model, what we'll see is initially a generator produces a very random noise outputs, which looks very much far apart from the real data. And it gets penalized by the discriminator, and over the iterations, the output of the generator improves. It improves progressively, the generator progressively becomes better at creating images that looks real, and the discriminator progressively becomes better at telling them apart. Till that time, they reaches an equilibrium where the discriminator can no longer distinguish between the real images and the fake images. And that time we say that the training of our model is complete. So we'll be using this, so we'll be using the same example to demonstrate this process on an MNIST dataset. As you can see on the following animation, it shows a series of images produced by the generator as it was trained for the 50 iterations. The image began as random noise, and it can increasingly resemble the handwritten digits over the time. So let's start with our code and let's see how we can generate this output. First, we'll start by importing the necessary TensorFlow libraries. In this example, we are using the TensorFlow version 2, and we'll be using the image.io API to create the animation. So once we have imported the library, we'll then load and prepare our dataset. So we as discussed, we'll be using the MNIST dataset to train the generator and the discriminator. So this generator will now generate the handwritten digits resembling the MNIST data. We have used the batch size of 256 in this example. So once we have loaded and prepared the data set, now it's time to create our model. So both the generator and the discriminator are defined using the Keras sequential API. The generator uses the Keras convolutional 2D transport layer to produce an image from a seed or a random noise initially. We'll start with a dense layer that takes this seed as an input, and then we'll upscale several times until we reach the desired image size of 28 into 28 into 1. Just notice in this that we have used the leaky rectified linear unit for our each layer except our output layer, which we use is a 10H. We have used the rectified linear unit, the leaky RE rectified linear unit to solve the dying rectified linear unit problem. So let's make our generator model. So we'll use this untrained model of the generator to create an image. As you can see, this is the image that is created using the random noise. And then we'll create our discriminator model. So in this discriminator model, we have trained to output positive values for real images and negative values for the fake images. Now we are going to define the loss functions and the optimizers for the both models. So here we are using the binary cross entropy loss function, similar loss function as we used in our previous examples. And we'll define our discriminator loss function. In this method quantifies how well the discriminator is able to distinguish real images from the fake images. It compares the discriminator's prediction on real images to an arrays of ones, and the discriminator predictions on fake images to the arrays of zeros. Okay, we have done that. And then we'll define the generator loss function. It quantifies how well it was able to trick the discriminator. Intuitively, if you think if the generator is performing well, then the discriminator will classify the fake image as the real one. And if it's not performing well, it will classify the fake image as with the zeros. So here we'll compare the discriminator's decision on the generated images to an arrays of ones. So the discriminator and the generator optimizers are different. So we'll train these two networks separately. And after that, okay. So here we have introduced the checkpoints and to save and restore our models. This thing can be helpful in case of running long training tasks and it gets interrupted in between, so that we can restore our last training model and we can use it to save time, and we can as well save our checkpoints in between. Here we have defined the number of iterations or epochs as 50 and number of examples to generate as 16. So after that, we will define our training step. Our training loop will begin with generator receiving a random seed as an input, and this seed is used to produce an image. Then the discriminator will then be used to classify these real images drawn from the training set and the fake images produced by the generator. This loss, this loss generated due to the difference of the images is calculated for each of these models. And then we are using gradients to update the generator and the discriminator through the back propagation. And we'll define our function train. And now we are defining a function to generate and save our images. So let's train our data set with the train function that we defined below, above. We'll call this train method defined above to train the generator and discriminator simultaneously. So note that in my experience, the GANs can be tricky. It's important that the generator and discriminator do not overpower each other. That is, they train at a similar rate. At the beginning of the training, the generator images look like random noises, as you can see. As training progresses, the generated digits will increasingly look like the real images. After about 50 or 60 iterations, they resemble the MNIST digits. So this one, in this training, it will take around 13 to 14 seconds for each iteration. And since we are running it for 50 iterations, so we'll be here for a while. Let's get back when the training is complete. So welcome back, and we are on the 49th iteration of the 50. So here it's taking around 13 to 14 seconds for each epoch, but if you go for the default settings in the collab, it might take around 1 minute. And here, as I can show you, our runtime is GPU. So we are able to do this process faster. So after this is done, this is our last iteration output. And as you can see, it's not perfect, but it still has started to resemble to the handwritten digits. So let's store our list. Let's restore our latest checkpoint. And then let's create our animation and see how the improvement happened. So I'm going to open this and I'm going to display our last step, and it looks like it's still not perfect. I think we'll either might be needing to improve our model, or we might need more iteration, but it has started to resemble to the handwritten digits. And we'll be using the image.io to create an animated GIF of this. And you can save, if you guys are working on the collab, you can save this uh, to your local desktop, and you can see how that thing pans out. So this tutorial was about the GAN, and I hope you got the basic understanding of what generative adversarial networks are through this example. Over the next videos, we'll be going in detail regarding more complex concepts. Till then, thank you.